Thanks a lot, Stephen, for the invitation. So today I will talk. A joint work with Mihai Pãun about the Ohsawa-Takegoshi extension theorem. So to begin with, I first explain a little bit our motivation. So in our talk, we suppose always that X is a projective manifold. In fact, for most of our rods can be, proved in the case of 1x is only weakly pseudo-convex. But for simplicity, in our talk, I always assume that X is projective. And now let Kx to be the determinant of potential bundle. So it's the canonical bundle of X. Now let Y to be a simple normal crossing divisor in X. And now let OY to be the natural holomorphic line bundle associated to this divisor. And now we fix a smooth Hermitian metric on this line bundle. And the third element is a holomorphic line bundle on X. And we suppose that its curvature is positive, and we suppose that its curvature satisfies some curvature conditions, which we will precise later. And now there is a very basic question: is that once we have a holomorphic section of this line bundle over the subvariety Y, and the first question is that could we extend it to the total space X? And the second question is that, if we could extend the small f to the total space, could we control its norm or not? So for these two basic questions, it's totally solved in the case 1y is a smooth divisor. In the case 1y is smooth, it's totally solved. In fact, in this case, it's so-called the Ohsawa-Takegoshi extension theorem. Now I just mentioned its local version. So to begin with, we suppose that omega is a weakly pseudo-convex bounded domain in Cn. Or for simplicity, we just assume that omega is a polydisk in Cn. And now let H to be an affine subspace in Cn, and phi to be a PSH function on omega. That means that phi is approximately continuous, and also its restriction on any complex lines in omega is subharmonic. Then in this case, given a holomorphic function on the subvariety H intersect with omega with the L2 condition, we can always find an extension to the total space omega such that its L2 norm with respect to this possible singular metric is controlled by some uniform constant times the L2 norm of the small f. So here, one remarkable point in this theorem is that for this constant here, it's in fact independent of the weight phi and the small f. So for this constant, it's quite uniform. And now since for applications in algebra geometry, we need some global version. So I think that for the first global version, due to the Manivella, here I always suppose for simplicity that X is projective for simplicity, and let Y to be some smooth divisor. So in this case, for the line bundle, holomorphic line bundle over X, we suppose that its curvature is semi-positive. And moreover, we need to assume that its curvature is a little bit larger than the curvature of the line bundle OY. So here I remember that for the metric on Y is smooth for simplicity, but for the metric on L it might be singular. anyway, so for the curvature condition, if the line bundle satisfies this, if the line bundle satisfies these two curvature conditions, then we can prove that for any holomorphic section over the subvariety such that its L2 norm is bounded. So here I would like to explain a little bit of the notation. Omega x is a Kähler metric on the total space X, so it induces a metric on the canonical bundle Kx. So therefore, we know that for this value, it's a positive function, and so therefore we know that for this integral is well defined. We suppose that its L2 norm is bounded. Then in this case, we can always find an extension of small f such that its L2 norm is controlled by this L2 norm. So here Sy is the canonical section of Oy. That means that it's the canonical. That means that it's the section of this line bundle which vanishes on the subvariety Y. And we need to add the normalization condition that its C0 norm is controlled by this constant, which depends on the delta here. And I would also like to explain a little bit these two L2 norm. Remember that F takes values in Kx plus L plus Y. So therefore, once we evaluated over the matrix of L and the matrix of Y, we know that for this one, it's a volume form. So therefore, this integral is well defined. And for the right-hand side, so for the quotient here, it takes values. So for the quotient here, it's well defined over Y. And by the canonical formula, we know that for the quotient here, it takes values in Ky plus OL. So for the quotient here, it takes values in the canonical bundle of Y tensors with L. So therefore, we know that so for this value, it's a volume form over Y. So therefore, for this term is well defined. And I would like to remark that in the case one Y is smooth, it's easy to check that these two norms are equivalent. The norm of this, it's easy to check that for this L2 norm is equivalent to this L2 norm. But in the singular case, one Y is not smooth. That means that Y, for our situation, Y is simple normal crossing. If Y is not smooth, then in this case, we'll explain later that for this integral is much singular than this integral, and in fact, by using Harmonic proof, we can prove that if for this one is bounded, say in this case, even in the case one Y is simple normal crossing, we can find the L2 extension. But for the assumption such that for this term is bounded, it's too strict for applications. I will explain this point later. So for this result, so for this Ohsawa-Takegoshi extension theorem is a very powerful tool in complex geometry. So for example, Mihai used the Ohsawa's local version to prove that any positive current can be approximated by the current with analytic singularities. And also in Tongxiu, he proved the invariance of Blue genera in the projective case. And later, Pãun, he simplified his proof. And more recently, Guan and Zhou, by using their optimal Ohsawa-Takegoshi extension theorem, they give a very simple proof of the positivity of their images. And more recently, and more recently Deng Wang Zhangzhou in their work by using the standard Ohsawa-Takegoshi extension theorem without optimal constant extension, they can also give the proof of the projectivity of their images. So in our talk, in fact, we are interested in the case when y is not smooth. That's but we always assume that y is simple normal crossing for simplicity. Well, we are interested in the case when y is not smooth. Why we interested in this question? Because it's closely related to the abundance conjecture, which I just mentioned. So for the abundance conjecture, it predicts that for any projective manifolds, if its canonical bundle is numerically effective, that means that its intersection with any projective curves in X is semi-positive. By using under this numerical assumption, abundance conjecture predicts that Kx is semi-ample. That means that we can find a fibration from X to some variety Y, such that Kx is just the pullback of some ample line bundle from Y. So for this conjecture, it's in fact a very crucial conjecture in birational geometry. At the moment, it's known only in the case when the dimension is less or equal than 3. For this conjecture, it's largely open. But in order to prove this conjecture, so there is one program. In fact, we can prove that for the abundance conjecture can be split into 2 sub-conjectures. One is non-vanishing conjecture. That means that the first step is to prove that under the assumption that Kx is natural, we would like to prove that Kx is Q-effective. That means that we can find a sun section after tensoring sufficient times. And the second step is to prove the following DLT conjecture. If we can prove the non-vanishing conjecture and the DLT conjecture, since it will imply the abundance conjecture. So for the DLT conjecture is as follows. Now we suppose that X is projective and Y is simple normal crossing, and B is some Q effective divisor. And now we suppose that the support of Y plus B is also simple normal crossing, and AI is less than 1. Now under the assumption that for the line bundle Kx tensors with Oy tensors with Ob, under the assumption that for this Q line bundle is NF, and also we suppose that it's Q-equivalent to some divisor, to some effect divisor D, such that it satisfies this inclusion. And in fact, in the paper of the Mihai Pãun, they can prove that for this inclusion, for this inclusion, it's in fact will imply the curvature conditions on L, which I have mentioned before. Under this inclusion, they conjecture that we have the surjectivity of this restricted map. That's true for any M sufficiently divisible. So to prove the conjecture, so to prove the abundance conjecture, a very natural way is to prove first a non-vanishing conjecture, and after that to prove this DLT conjecture. But unfortunately, to prove this conjecture, it's still unknown. In fact, in the paper of the Mihai Pãun, they proved the DLT conjecture under the assumption that when Y is smooth. Under the assumption that Y is smooth, so in this case, they can use the standard Ohsawa-Takegoshi extension theorem, and together with the techniques together with the techniques in the proof of invariance of liquid genera, they can prove the DLT conjecture under the assumption that 1y is smooth. So therefore, if we want to prove the 4 DLT conjecture, a very natural way is to generalize the Ohsawa-Takegoshi extension theorem to the case 1y is simple normal crossing. So that's the main motivation of our works. Now I would like to explain a little bit our results. So for the first result is that so for the first question is to ask if under these 2 conditions could we find the same extension or not. For this first question, it's in fact it's not very difficult. So in our paper, with Mihai and Matsumura, we prove we can give a positive answer to the first question. So still under this curvature condition, and the letter F to be a holomorphic section over the subvariety Y, which is might be no smoother. And also we assume that its L2 norm is bounded. And also we assume that it should admit a local L2 holomorphic extension, which I will explain later. So in this case, we can prove that we can find a holomorphic extension and we can control its L2 norm. But unfortunately, we cannot prove that for this L2 norm is bounded by some uniform constant times the L2 norm of F. So for our result, it's not for our result, so we could not provide an effective estimate on its L2 norm. So let me first explain. So let me first explain this condition. So for holomorphic section F over Y, we say that it satisfies L2 holomorphic extension condition. That means that at least locally we can extend small f to its small neighborhood as a holomorphic section, and such that such that for the Fi its L2 norm is bounded. So for this condition, it's in fact a necessary condition. It's in fact a necessary condition. In fact, later I will explain that there is so in fact later I will explain that there is an example of Ohsawa who told us that if we just only assume this condition, then it's possible that we could not find a local L2 extension. I will explain later. So for this condition, it's so for this condition is necessary. But unfortunately, in our work we cannot control the L2 norm effectively. So therefore, to answer the second question, to find an effective estimate, it's very difficult. It's in fact very difficult. Let me explain a little bit the difficulty. In fact, as I explained before, if we assume that for this L2 norm, recall that Sy is the canonical section of Oy. So therefore, for the quotient here, it takes values in ky plus L. In fact, even in the case 1y is simple homomorphic crossing, if for this L2 norm is bounded by using the same proof of Lohan-Manivela, we can in fact find an extension such that its L2 norm is controlled by this L2 norm. But unfortunately, for this condition is not very natural in bidirectional geometry. In fact, we can prove that. In the case 1y is not smooth. For this condition, it's a very natural. For this condition, it's a very natural condition in algebraic geometry. But for the finiteness of this L2 norm could not imply the finiteness of this L2 norm. So for example, if we take y to be a normal crossing divisor in C2, and if for the small f it not vanish on the central point 0, 0. So therefore, we know that for this integral, it's equivalent to the L2 norm with respect to the smooth matrix quotient by Z1 square plus Z2 square. So therefore, if in the case one, one for this term, if in case for this term is not equals to 0 on the central point, for this integral equals to for this integral it in fact equals to infinity. So therefore that explains that for this condition it's in fact very restrictive for applications. Now I would also like to explain. So now I would like to explain a result of Ohsawa, who tells us that in fact if we want to find an effective estimate of if we want to find an effective estimate for the extension section for this condition, for this L2 condition is not sufficient. As I explained before, for this condition is too restrictive. But the Ohsawa's example will tell us that for this condition, for this L2 condition, is not sufficient. So that's the second example of Ohsawa. And as before, we take y to be the normal crossing divisor in C2, and phi L to be so let phi L to be a PSH function of the type log Z1 minus Z2. So in this case, now we let small f to be a holomorphic function on the on y, which is equals to 0 on one component and equals to Z1 on another component. It's easy to see that for this L2 norm, so which corresponds to this L2 norm in the global case. If say in this case, it's easy to see that for this L2 norm is bounded, but however, we could not find an L2 extension. That means that we could not find a holomorphic extension such that its L2 norm is bounded. Why? Because if we assume by contradiction that we can find a holomorphic extension and such that its L2 norm is bounded, then therefore by the truth of this matrix, we know that for this integral is bounded. So therefore that means that for this for this meromorphic function, it's L2 bounded. So therefore it's holomorphic. But by using this boundary condition, that will implies that for the quotient here it's equals to 0 on one component, and the second boundary condition implies that it's equals to 1 on another component. But for these two components, they intersect on the central point, so therefore it's impossible. So that means that so in general, if we just assume that for the small f satisfy this L2 condition, it's not sufficient for applications. If you don't like the singular matrix, we can also take a smooth approximation of this singular matrix. Saying in this case, if we can find a holomorphic extension with a uniform on its with a uniform control on its L2 norm, then in this case, by letting epsilon tends to infinity, that will imply that for the limit, its L2 norm is bounded. so it contradicts with Ohsawa's example. And also, I would like to remark that it's easy to construct a global version of Ohsawa's example by tensoring some ample line bundle. So by using Ohsawa's example, it tells us that for the standard L2 condition, it's not sufficient for us to find an L2 extension. So therefore, in our paper, we proposed the following conjecture, which says that in fact we conjecture that in fact if we add a little bit more stronger condition, then we guess that it should then we guess that we could find a holomorphic extension. So for our setting, we still assume that X is projective, Y is simple normal crossing, and for the line bundle L, it satisfied the standard curvature condition, as I explained before. Now let V singular to be a singular. Now let V singular to be a neighborhood of the singular locus of Y. To be the singular locus of Y. So therefore, since Y is simple normal crossing, for the singular locus is of codimension at least 2. So for this part, it's a neighborhood of some codimension at least 2 subvariety. Saying in this case, we conjecture that for any small f, which a holomorphic section on the subvariety with the standard L2 condition, and we assume that at least locally, we can extend it as a L2 section. So in this case, if under the assumption that for this term is finite, so in this case, we can find the extension such that its L2 norm is controlled by this one. So let me explain a little bit the right-hand side of this inequality. So for the right-hand side, as we explained before, for this quotient, as we explained before, in the case 1, Y is smooth. So in this case, for this L2 norm is equivalent to this L2 norm. So therefore, for the first term on the right-hand side, since it's outside the singular locus of Y, so therefore, if this one is so therefore we know that for this L2 norm is bounded by this L2 norm, and here we need to add another L1 norm. That means that close to the singular locus of Y, we need to assume that for this L1 norm is bounded. So for our conjecture, we state essentially that if we assume that for this L1 norm is bounded, so in this case we can find an extension with a control on its L2 norm. And I would like to remark that, if we could prove this conjecture, then we could probably prove the DLT extension conjecture in the case 1, Y is simple normal crossing. And also, I would like to remark that it's easy, and also I would like to remark that here for the metric HY here, we can suppose at the beginning that HY is of simple normal, for the HY is of analytic singularity. Yeah. So at the moment, we could not prove the conjecture for full generality, in fact, at the moment, we don't know whether our conjecture is true or false in full generality. Maybe you can find some counterexample of this conjecture. It's also possible. But at least in our paper, we could prove a special case of our conjecture. If for the weight of the major, if weight so phi L is the weight of the single matrix, if for the weight on a neighborhood of the singular locus of y is of this type, that means that it's of the type log s square. So here s is any holomorphic function on V, and plus some conic type of singularity, and plus a bounded function which satisfies this curvature condition. Say in this case, we can prove our conjecture. So, so that's the main theorem of our paper. That means that if for the matrix is of this type of singularity, and its curvature is at least c times the conic matrix with respect to this divisor. So in this case, we can find an extension such that its L2 norm is bounded. But for our results, it's not sufficient to prove the DLT conjecture. Okay, so in the last part, I would like to explain a little bit the proof of our theorem. So for our theorem, it depends on a lemma of Ying-Hong-Su, and it depends on it depends on a lemma of Ying-Hong-Su and the argument of Bo-Bedson. So let me state the lemma as follows. Now we assume that X is a projective manifold of dimension n, and for the line bundle L, it satisfies the curvature condition as before. It satisfies this curvature condition. Saying in this case, for any smooth N1 forms C with values in L, we have this inequality. So for the star here is the Hodge star operator, which sends the N1 forms to N-1 zero forms. So for the left-hand side, is in fact the L2 norm of stack C over the subvariety Y. So Y is of complex codimension 1. And they can prove that in fact for this term is less than some uniform constant times the L2 norm of the derivative of C. So for this result, it's in fact a very, very strong result. So for this result, it's in fact a very strong result. That means that if for the line bundle L satisfy our curvature condition, so in this case, we can bound the L2 norm on the subvariety of real codimension 2 by the L2 norm of the derivative. It's a very strong result. So since we have not enough time to prove the lemma, I would just like to explain the idea of the proof. So now we just take C to be the n-1 form, defined as follows. Now Ying-Hong-Su, he proved that dd bar of C is in fact equals to this form. So therefore, to prove this inequality, so therefore, in order to prove this inequality, we now calculate the integral of C with the dd bar of log sy squared. So for the residual part of this integral, it gives exactly the left-hand side of this inequality, and for the right-hand side of the we just use the Stokes formula, and also this equality we can easily obtain that for this term is controlled by this term by using this formula. So that's the idea of this proof. So that's the idea of the proof of the lemma. So now I would like to explain a little bit the proof of our main theorem. Now to begin with, we use the standard L2 estimate technique. Now let Xi to be a smooth N1 form. X is of dimension n. Xi to be a N1 form with values in L. And now we consider the Hodge decomposition of Xi. Xi can be split as Xi1 plus Xi2. So here for Xi1, it's d-bar closed, and for the Xi2, it's in the image of d-bar star, so it's d-bar star closed. And by using our result, we have already know that under our curvature condition, we can find an extension, but we could not control its L2 norm. So in any way, so for the d-bar of this term is a current supported in Y, and now we consider this product. Now we consider this product, and we recall that for the C2 here by Hodge decomposition, it's in the image of d-bar star. So therefore, even in the case for this one is only current, we can still prove that its product with C2 equals to 0. So therefore, for this product equals to the product with C1, and since it's current supported on Y, we can calculate it explicitly, and for this product, it's just equals to this term. Now we would like to control the norm of this integral. In the case 1, Y is smooth. In the case 1, Y is smooth for this integral is very easy to control. Why? Because we just apply the Cauchy inequality to this integral. We know that for this one is controlled by the L2 norm of small f times this term. As I explained before, in the case 1, Y is smooth. For this L2 norm is equivalent to the L2 norm in the condition. So for this one is finite. And for the second term here, we can apply the lemma of Superbedson. We know that for this term, its integral over Y is controlled by this one. So therefore, for this term is controlled by the integral of the derivative of Xi over X. But as we explained before, by using the Hodge decomposition, Xi1 is d-bar closed. For this term equals to 0. For this term equals to 0. And for the Xi2 here, it's d-bar star closed. So therefore, d-bar star Xi1 is just equals to d-bar star Xi. So therefore, we know that for this product is controlled by the L2 norm of small f times this term. So therefore, by using Ritz representation, we know that we can find some mu such that we have this equality for any Xi, and we have a control on the L2 norm of mu. Since we have this equality for any Xi, so that means that d bar mu equals to d bar of f over sy. By using this equality, we know that if we define f theta to be mu times sy, then in this case by using this equality, we know that f theta is holomorphic, and it extends the small f. And for this L2 condition, it implies that the L2 norm of f theta is controlled. So that's finished the proof. In the case 1 y is smooth. That means that in the case 1 y is smooth, for the Ohsawa-Takegoshi extension theorem, it's in fact a direct consequence of this lemma. So yes, so for this one, it's essentially the proof of Bob-Edison for the Ohsawa-Takegoshi extension theorem. Now in the case, now in our case, why is now in our case the difficulty is that y is not a smooth, y is only simple normal crossing. So therefore, for this term, is not bounded. So in this case, how we can prove it? Now in our case, we didn't take any C. We just take the C which is supported outside the V. So here V is a small neighborhood of the singular locus of Y. The singular locus of Y is of codimension 2. C is supported outside V. So in this case, we still consider the Hodge decomposition of C. And we suppose at the moment that for this product, in this case, we can control this. If we can control this this product by some constant depends on f times this term. For the constant which depends on the small f, it's in fact it's just equals to the right hand side of our conjecture. So for the C small f is in fact for this is in fact just equals to the sum of this one plus this L1 norm. In fact, we could prove that for this product is controlled by this C small f times this term. I will explain later why we have this inequality. If we can prove this inequality, for the rest part, it's in fact very simple. Why? Because in this case we can by Ricci representation we can always find some mu such that we have this equality, and also since we have this equality for NXC which is supported outside of the V, so therefore we know that so therefore by the argument as before we know that mu times Sy is a holomorphic function, is a holomorphic section outside of the V. But we recall that V is a small. But we recall that V is a small neighborhood of the singular locus of Y. So that means that we can in fact apply the Hart-Gauss on this variety. So we know that it can be extended as a holomorphic section on the total space. And its L2 norm is controlled by CF, since for the L2 norm of mu is controlled by the CF. We can control this, the L2 norm of this holomorphic section. So let's finish the proof. So therefore, in the last 5 minutes, I will explain why we have this inequality. So as before, for this product, it equals to the integral of small f over dsy, which is stack C1 over the subvariety y. Now we split the integral in two parts. One part is outside V. Another part is over the set V. So here V is a small neighborhood of the singular locus of Y. For the first term, it's in fact on the locus where Y is smooth. So therefore we can estimate it as in the case 1Y is smooth. That means that by Cauchy inequality we know that it's controlled by this term. And by using the lemma of Sue-Bedson, we know that for its L2 norm is controlled by the L2 norm of this one. So for the estimation, on this part, it's the same as before. Now the difficulty is to control the L2 norm of this integral near the singular locus of Y. So how we can control it? Now the trick is that in fact for the function for the test function C, it's supported outside V. So therefore we know that C1 equals to minus C2 on V. We recall that C1 is dbar closed. For C2 is dbar star closed. So therefore we know that for the dbar star of C1 by using this equality, we know that dbar star C1 is equals to minus dbar star C2, which is equals to 0. So therefore, in fact, for C1, it's dbar closed and also dbar star closed. So that means that C1 is in fact a harmonic. Now, by using the harmonicity of C1, we can control its C0 norm under the assumption that for the singular matrix it's of under the assumption that for the singular matrix is of our type singularity, is of this type singularity. We can control its C0 norm by using the harmonicity. We can control the we can control its C0 norm by the L2 norm of dbar C by the L2 norm of dbar star C. So therefore, once we know that for its C0 norm is controlled, we can control this integral. It can be less than the L2 norm of the quotient times this term. So once we can prove this inequality together with this inequality, we know that we have this inequality for the product. So that's finished the proof of our theorem. Thank you.
Thank the speaker. Maybe we can show our clapping. There's a clapping. Are there any questions? So, Junyan, just in the last part, when I'm just curious in the simpler situation where the singularities are just points, in the case of surfaces.
Yeah. So you mean that it's in the case of 1x is of dimension 2?
Yes, yes. So that's a very easy case.
Yeah.
I don't think you need some serious assumptions to bound things like that, right?
No. In fact, I think that so for this point, so for this case, it's also it's also difficult for us since in this case, so for the phi L here, even in the dimension of 2, so for PSH function of analytic singularity, so quite so for the singularity, it might be very complicated in the dimension of 2 case.
In the dimension 2 case, I assume you can relax the condition a bit, right? No.
At the moment, we don't know we don't know how to remove this condition because in this case for our constant here, it depends on the geometry or it depends on the geometry of this conic matrix. So so once the singularity so once the serial locus of this section is very, very complicated, we don't know how to control the geometry of it. So that's the main difficulty. So I mean that I just means that in a dimensional two case, once it's near the central point, so for the zero locus of this one of this section is very difficult. Is very complicated. We can always find some local curve such that its volume becomes such that it's smooth, but its volume is very large. It's totally possible. So in this case, so for this canonical matrix is very complicated. We cannot control the geometry of it.
I see. So already difficulty is already in dimension 2.
Yeah. So for dimension 2, I think that it's the main difficulty.
Main difficulty, okay.
Oh, hi, I have a question.
Valentino.
I remember you have some earlier result, also the Mihai for when y is non-reduced.
Yes.
Is there, I mean, here you assume reduced, right? In this current.
Yeah. So in fact, so for our route, with the Mihai
and Matsumura, right?
Yeah. So for our route with Mihai and Matsumura, we don't need to assume that for the sobriety is non-reduced. But in our case. But in our case, we really need to assume that we really need to assume that so for y is simple normal crossing because I think that so there is some results of Paul Beckson who tells us that in fact even in the case y it's x is of dimension 1 and y is a double point, so we could not so in general we could not hope we could not hope to find some well estimator. So Mihai he just so in fact in this afternoon Mihai he just mentioned a paper of Anderson who proved the same extension theorem. Who proved the same extension theorem in case when the subroutine is not reduced. But I have not yet read carefully his paper. So I think that so maybe by using his route we can prove something, but we have not yet considered it.
Which one is Mats Anderson?
Yes.
Oh, okay.
Yes.
Thank you.
Yeah. So for his paper, it's in this year, in April, I think. He also for his paper in April. I have not yet read his paper.
Thank you.
Okay. There are numerous results now, which are interesting. So the extension theorem. Once you have these hypotheses satisfied, you do have the extension theorem, I guess, and you can more or less prove the extension.
Yes.
Yes. I think these restrictions in practice maybe not so bad. I mean, are there good applications with these type of restrictions?
Yeah. So in fact, we have tried to find that we have tried to find some applications, but at the moment we have not yet found some satisfied applications. We are not doing something, but it's not clear at the moment.
Of course, you have to do restrictions in some sense. I mean, there are no general results.
Yes.
No general results.
Yeah. So so the main restriction for our RTA is that so for the main restriction of our RTA is that so for our constant here, it's in fact it depends on the geometry of this conic metric. So that's the main problem. Yeah, since if we do by induction, so in general we cannot control the zero locus of this section. So that's the main problem.
So we're almost an hour, and maybe let me ask again if there's any other questions for Junyan.